So this is the part 3 of the electrical circuits chapter, and today we are doing the numericals of potentiometer, then galvanometer and all these. So we are completing this in this video. So first of all, let's start off with the remaining numericals from question number 6. We were in question number 6 in the last video, so we are going to start from question number 6. I basically rage quit in the last video, so yeah. Okay, let me just adjust some lighting. Yes, I think this much is good enough. So 6 or 1, this is at 1. The question is already written in the last video, so I'm not going to write it again, and go and watch it if you have not. The question has given us E naught equal to 2 volts. The resistance internal is given 0. The resistance of the potentiometer is given 3 ohm. The potentiometer voltage, the voltage across it is given 5 millivolt. You can convert it as simply, and that will come out to be 5 × 10 to the power minus 3 volts. And we need to find the value of R, the resistance that was added to series. So we know that, first of all, what do we know is current equal to E by R, and this will be equal to E by R plus RP plus R. So this will be 2 by 0 plus 3 and R plus 3. This is the equation 1. Again, we also know that current V equal to IR. We know that V equal to IR, and this is for the potentiometer wire. So the potentiometer wire 5 × 10 to the power minus 3 is equal to I is we need to put the value from equation 1 into RP is 3. So if you do the necessary calculations, you will find the R value to be 1197 ohm. We calculated this in the last video. Now after that, we are given LP, the length of the potentiometer is 100 centimeters, and the length after the only for the cell is 60 centimeter. From the second law, we know that the first application to compare the second application to find out the EMF, we use this. So it is like this. Yes, L by LP. So if you do this, we just go E. We need to find the value. We have the value of E, that is no, we need to find the value of E, my bad. E, we need to find the value of E, and this is E equal to what, by the way? Yeah, okay. Now E equal to L into Vp by Lp. If you put all the values, the answer will come around 3 × 10 to the power minus 3 volts. This is how you do it. Now another question very important for your exam is here, right here. Let me copy the question again. There it is, the question. So a potentiometer wire is 10 meters long. L equals to 10 meters. The potentiometer wire is 10 meters long. It has a resistance of 20 ohm. So the potentiometer resistance is 20 ohm. It is connected in series with a battery of 3 volt. So the battery is 3 volt. The resistor of R equal to 10 ohm. What is the potential gradient? So this is a very simple question. You can just use the same thing we did the last time. First, calculate the current by doing R plus RP, because internal resistance is not given here. So you just do 3 by 10 plus 20, that is 3 by 30, that is 1 by 10 ampere. Now that we have I, we can easily calculate the Vp, that is the potentiometer voltage, so that will be 1 by 10 into 20 is the resistance here. This will be 2 volts. So after you find out this much, you can now just use the formula for the potential gradient. We know that potential gradient is, what is potential gradient? It is Vp by L. It is 2 by L is 10. It is 1 by 5, that is 0.2. And the unit is volt per meter, of course, volt per meter. That's the answer. Very easy, very easy, right? Now we're going to question number 3. This is the last question, and let me copy the question. Okay, here is the question, and there is a circuit given, potentiometer circuit, just like this, with a jockey right here and a galvanometer like this. This is the jockey, and this be the C point, and these are A, B. This is the E with positive and negative E naught, and the resistance here is 2.5 ohm as given. So, and this is E, which is 1.5 volt. So to solve this specific question, it is a very easy job. So first of all, you need to understand what it's saying. A simple potentiometer circuit is set up as shown in the figure using the wire AB of length 1 meter. So what is given? LP is 1 meter, having resistance of 2 ohm. RP is 2 ohms. A battery of 4 volt is provided, and the value of we have E equal to 4. Okay, that's E naught equal to 4 volt, and is equal to 4 volt. And what else is given is and the value of R is 2.4, 2.5, I think 2.4 ohm. What should be the length of AC? So we need to find the length of AC, this length, for the thing, that is L equal to what? The length L is what? So this is also a same question you are seeing here, and let's go, let's do this, let's solve this. Now you can see the question properly here. Now, okay, then we go to the next page. You can see the question just like that, and here is the given. So we know that I will be equal to E by R plus RP. So this R is not given actually. So E is 4 upon R is given 2.4 into 2.4 into this 0 plus 0. Oh, this is 2.5, my bad. This is 2.5. Okay, this is 2.5. This is 2.5 plus 0.0 plus the RP is 2, that is 4.5. So 4 upon 4.5, let me put it in the calculator. 4 upon 4.5, 0.89, as you can see, 0.89 amperes is the current. Then we again know that again Vp equal to I into Rp. So Vp we have been given, no, we have not been given. Vp equal to I is, what is I, what is 0.89 into Rp is given 2 ohm. If you multiply this by 2, you get, or Vp equal to 1.78 volt, and again now we are asked to find the equivalent point, and we need the length. So for the null deflection, that means it is an equivalent point, and that is a application of potentiometer. As you can remember, the law of potentiometer says that E equal to KL. So we need K to find the L. So K, the potential gradient, will be equal to the voltage per unit length. So LP, we need that. The length of potentiometer is 1 meter, that's given. So Vp we found out is 1.78. by 1 will be the same 1.78 volt per meter. That is the potential gradient. Now from principle of potentiometer we have E equal to KL, we know that, and E is given 1.5 volt. So we can use 1.5 equal to K is 1.78 into L. So L will be equal to 1.5 by 1.78, and if we put divided 1.5 by 1.78, we get 0.84 meters, which is the answer. Now we have completed the numericals of this chapter as well. So now to moving to the next topic, and the next topic today is galvanometer. Yes, we're going to galvanometer and let's first define it, and then we'll learn how to convert it to different devices such as ammeter and voltmeter. So first of all, let's define the galvanometer. This won't be action or examination, but you need to know. Galvanometer is a device used to detect small current flowing through the electric circuits. So yes, that's how you define a galvanometer. Now you can convert a galvanometer to two devices. First you can convert it into an ammeter. Second, you can convert it into a voltmeter. Conversion of it into, okay, so let's understand how can it be converted into ammeter and voltmeter. So first of all, galvanometer needs to be connected to a shunt to be converted into an ammeter. So a shunt is a low resistance device, right? Let me check in the book. Yes, shunt is a low resistance that is converted to galvanometer in parallel to the in parallel. The figure looks like this. This is the low resistance. This is the galvanometer. And it is connected in the circuit, like it is connected in the circuit in the parallel, so it should be like this. I comes here, Ig goes down here, Ig goes up here, and I comes up here. That's how it should be. And it is always ammeter is connected in series in the circuit. This is the ammeter. It is connected in series in the circuit. The value of S shunt value, the S value can be found out by, it gets divided here, IS, by the way. So it can be found out as the Kirchhoff's, the potential difference. You just equate the potential, so you equate this to this, because this must be equal to this, because that's the only thing that can happen. So look at this, the current goes, if these two are connected in parallel, look at this, the potential in these, both of these must be equal for the current to flow through them equally. So I is, right? So I, you can just write is or I minus Ig, just write I minus Ig right here. Okay, so I minus Ig times S will be equal to Ig times G. If you find S, it will be Ig upon I minus Ig times G. This is the relation for it, and it is also called, the device is also called an ideal has zero resistance, just like that. That is ammeter. Now voltmeter. Voltmeter is an electronic device that is formed when a multiplier, a very high resistance device called multiplier, is connected to the galvanometer in series. I mean in parallel. Yes. Mm, okay, no, in series. Yeah. Galvanometer can be converted into a high in a voltmeter by connecting a high resistance, also called a multiplier, in series with the coil of galvanometer. Yes. Yes, 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 yes. It is connected in parallel to the circuit across the conductor. So, first of all, multiplier of a high resistance device that is connected to galvanometer in series. How does this look like? It looks like this. The whole system is connected in series, however. G R I G and I goes here. So voltmeter so potential difference across the voltmeter must be equal. So the voltmeter, the thing here, what happens here is the potential, the V, the total potential V is equal to, because if you assume it, the upper thing to be V, the potential here be V, then it should be Ig times G plus R, and from that V by Ig minus G equal to R. That is the equation for finding the resistance or the value of or the strength of the multiplier, just like that. And an ideal what is it, voltmeter has infinite resistance. You need to understand these two terms to be able to do it. So yup, look at that. Okay, now we have completed the ammeter, voltmeter, galvanometer conversion, everything. So now the next thing is the numericals, and the numericals I'm skipping it because that is not very significant if you ask me. You just use the formula, so I'm skipping the numericals. And The thing that now remains, let me check the book, is the ohmmeter, Joule's law of heating, and some definitions of superconductors and perfect conductors. So, okay. So, okay, first of all, we're going to ohmmeter. What is ohmmeter? Ohmmeter is a device, it it clearly says ohmmeter, a device used to measure the resistance of a conductor or ohmic conductors, the conductors that follow Ohm's rule. So if that's the thing, then now we're going to Joule's law of heating. The statement of this law is very simple. The amount of heat developed in a conductor, the amount of heat developed in a conductor due to the flow of electric current through it is, at number 1, it is directly proportional to the square of current, that is H is in directly proportional to I square. And number 2, we have directly proportional to the resistance of the conductor, that is directly proportional to R. 3, we have directly proportional to the time for which current was passed, that is H is directly proportional to T. So on combining, now we have H is directly proportional to I square RT, and there is a constant, that is H will be equal to I square RT upon J, and the J is Joule's mechanical equivalent of heat. The value of J might be asked in MCQ is 4.2, you can say 4.2 joule per calorie. It is the unit used to convert the values, the SI and CGS unit of joules as well. So you can do that. Now for the expression derivation, it's a very simple concept. I'm going to explain you shortly. So yeah, let's go for it. Let's assume a circuit like this, a conductor, let's say, and there is a EMF right here. The I goes from here and comes back here. The resistance is between the two points A and B, like that, and the potential difference here is V. So what do we already know here is the formula of V, that is IR. We know it, the current flowing through the conductor, that we know it. So this is the equation 1, we know that much. Now let's suppose the current I, this current passed through the conductor for some time t. Then suppose we just need some charge relation. Suppose I was passed for t, then we know that charge current equal to charge by time, so charge will be equal to q will be equal to it, because uh, I will be equal to q by t, we know that. So again, v is equal to w by q, we also know that. So if we know that, then we can do it like qv equal to w, the potential, by the way, we know that, right? We can do that. Now from these two equations, you can see we can put the values of things. So or w equal to q into ir. So again, w equal to ir into it is q. Look at this from equation 2. From equation 1 and 2, or w equal to I square rt. This is the equation 3. Now w in terms of calories, this is in calories, so if you want to turn it into joule, you can write h equal to I square rt, simply 4. You can just write that. That is how the, okay, and by j also, by the way. Yeah, that is how you derive the equation, and that's it. You do it very very easily like that. So now we have two small definitions and the chapter is also over. So the two small definitions are perfect conductor and super conductor. This is the ideal conductor. A conductor having zero resistance is called perfect conductor. Its conductance is the highest, so it is not possible, so it is ideal. However, a conductor having zero resistance below the critical temperature is called superconductor. It is used in supercomputers now. That's what you need to remember, and that is all you need. It won't be asked any more than that. So the video ends here. The topic, the chapter, look at this, the chapter uh, 14 is completed. We did all of them, and if you have any confusions regarding this, you can just comment out every day. You can email me or whatever, you can do it. So yeah, see ya.